Hey everyone, we're gonna get started in about one more minute. All right, is my screen visible to everyone? You could type in the chat. Great. All right. Hey everyone, my name is Mihir Mathur. I'm one of the product managers here at Tecton, and I work closely with a few different teams at Tecton. One of them is the embeddings team. We've been working on for the past about a year on our embeddings initiative, and I'm really excited to talk to you about production embeddings for business critical, predictive, and generative AI. So I'll be talking about a few different things. We'll start with a very quick primer for embeddings. Then I'll walk through some business critical embeddings examples from leading tech companies that we've seen in the industry. I'll walk through some of the production challenges that we've heard from our customers and prospects and just in the industry in general. Then I'll give a quick overview of our embeddings offering, and finally we'll have some time for questions. All right, so let's get started. So let's start with a very, very quick primer on what embeddings are and why are they important. So what are embeddings? Embeddings are condensed numerical representations of data, which can be text, images, audio, or it can be any other structured data as well. So in this example, there is some unstructured text, which is these city names as well as airplane, horse, and animal. So all of these things can be represented in a numerical way by assigning coordinates in this three-dimensional plane. And as you can see, the words that are similar are closer together, whereas the words that are dissimilar are farther apart. So in this example, an embeddings model would encode these words into three-dimensional number vectors. So for example, New York could be 2, 3, 1. So that would be the X, Y, and Z coordinates, whereas Beijing could be 3, 2, 0.5. And words that are more similar are more closer together in this three-dimensional plane. So how are these embeddings generated? Embeddings are generated using specialized encoder models, which are typically neural network based. And those models are trained on large data sets to learn the patterns and associations. So these models will go over large set of words, phrases, or images, or any other type of input that they have to encode and learn the patterns and associations. And then they can map the input data to a high dimensional vector space. Another way of thinking about embeddings is that they're just the AI's language for communication. That's how AI understands what the semantic meaning is for different words. So what makes an embedding a good embedding? So good embeddings have a few different characteristics. They capture relevant semantic information. Similar items are close together in the embedding space, whereas dissimilar items are far apart. And embeddings enable meaningful comparison and operations. So there's just some of the good properties of defining a good embeddings model. And I want to expand a little bit on the last one. So what does it mean to compare and operate on embeddings? So there are a few different similarity operations. So you can look at the Euclidean distance, which would just be the straight line distance between two different points in the vector space. You could look at the cosine similarity, which is the angle of the relative angle of the two different embeddings. And you can look at the dot product of the two different vectors. So these are some of the common metrics that people use for comparing different embeddings. Now let's take a look at some of the business critical embeddings examples. So over the past 6 to 8 months, we've been talking to a lot of people in the industry, and also just looking at people who have published blog posts about embeddings. So I went ahead and collected 5 examples that I think are really great examples of showing embeddings in production for very core business critical use cases. So I want to start off with an example from Lyft. So this is actually a use case that I was pretty familiar with. I used to be a product manager at Lyft till early 2023, and I was on the machine learning platform team, building the core foundations for Lyft marketplace pricing, fraud detection, and such. So one of the projects that the applied machine learning team was leading at Lyft was Lyft to Vec, which was Lyft to vectors. So that's basically embeddings at Lyft. So in this example, the what the team was attempting to do and were successful with was representing driver and geohash 6 embeddings. So drivers, you all understand. Geohash 6 are these geometrical markers for every single piece of land. And so what they were trying to do is identify patterns of similarities between drivers and locations. And so what that means is, let's say a driver prefers driving in certain hours of the day. Let's say they prefer driving in the morning. And there are certain geohash sixes which have a lot of demand or requests in the morning. Then the driver and that location would be more similar. So in this diagram, the higher scores have a higher similarity between the driver and the location. And so how they were using these embeddings was for marketplace matching, because if you can better match drivers with locations that they're similar to, then you'll have a better accept rate, better trip success rate, just more efficient matching, and it just contributes very directly to your both top and bottom line. So this was a very critical, business critical core embeddings use case. Another use case which is very critical is fraud detection for Stripe. So Stripe is in the payment space. One of their biggest challenge is detecting fraudulent payments, both on the consumer side as well as on the merchant side. So from this blog post written a couple of years ago, they talk about how they use merchant embeddings to look at the similarities and differences between different merchants. So in this example, they illustrate the embedding coordinates of 3 different merchants on Stripe, so Uber, Lyft, and Slack. And you can see the Uber and Lyft's coordinates are similar, whereas Slack's is different. And the way they use these embeddings is they look at patterns of merchants who they know were fraudulent in the past, and any new merchant who gets added on or is malicious can get flagged because they're more similar to other fraudulent merchants. So this is another example of a very business critical core use case for Stripe. Every 0.1% difference in fraud rate matters to them a lot, because that really affects their bottom line. Another example of embeddings in a business critical use case is this use case from eBay for product recommendations. In this use case, eBay is using multimodal data to better express listings. So, what does multimodal mean here? That means using the text, using the images of an item. There might sometimes be some video of the item. So they want to use all of those, that rich unstructured data, to express into a numerical representation, which they can then use for better product recommendations, both for when you're just scrolling and for when you search something. So this is also a very core use case to how their business works. Another example of a very critical use case of embeddings is embeddings for search. And in this example, Instacart is using embeddings to improve search relevance. So when you go on the Instacart app and search for, let's say, a grocery item, they use this model under the hood, which is called items, the Instacart transformer-based embedding model for search. So that's a deep learning model that can jointly learn the representation of queries, products, and their relationships. So you might have a query which is oranges, and their grocery store might only have clementines, but you'll still get that result because they have learned that those words are similar. So this is a very important use case for Instacart because this is how people add things to their cart and buy on Instacart. I also want to just pause and just look back at all these four examples that we've discussed so far. All of these were actually predictive AI. So there was nothing being generated at the end. The only thing that was being given to the user is either a ranking or a price or a matching order or a classification. So all of these are predictive AI tasks, and there's been heavy use for predictive AI in for embeddings. The last example is more for retrieval augmented generation. So Glean is a company which provides enterprise search. So it's sort of a Google for your own enterprise data. And Glean has published a few different blogs on how they use embeddings for vector search and for RAG, which stands for retrieval augmented generation, in which you first retrieve similar text or items, and then you augment a generative model to give very high context responses. So one thing that struck out to me in this example was Glean said this line that in enterprise search tasks, open source embeddings such as E5 Large, Instructor XL, and MPNet still outperform the embeddings provided by commercial API providers such as OpenAI and Cohere. So open search embeddings models beat the commercial embeddings models. So this has also been consistent in what we've been seeing at Tecton and what we've been hearing from other customers. All right, so these were examples of these leading tech companies who have invested a lot of work, a lot of resources in getting embeddings into their most business critical use cases. But over the past six to 8 months, we've also been talking to other customers who are in other different places in their embeddings journey. So I want to present this as the sort of high-level framework in how we're thinking about enterprise readiness for embeddings. We have seen companies who we think are going through these 4 different stages. So some companies are in the early interest and experimentation phase. So a lot of these companies who have just started working with AI after the whole Gen AI wave are building these low-friction prototypes. They leverage open source. It's just a prototype to get internal buy-in from stakeholders and just to prove that this proof of concept would have some business impact. So that's stage 1. And this obviously has low value in terms of delivering business impact, but it is a very necessary stage to just get further investment in productionizing these use cases. The second set of use cases we are seeing are internal use cases. So we call them auxiliary use cases, where the productivity of just internal team members is optimized with embeddings. So these use cases are things such as internal documentation. So a lot of companies, including Tecton, has just extensive internal documentation on how to how to develop things, how to for like HR queries, for other support queries internally. And embeddings can really help with retrieval augmented generation use cases similar to Glean. And people are trying to just build that on their own. So these use cases are internal but important. The third pattern that we're seeing, third stage in this value graph that we're seeing, is disconnected production use cases. So this is when there's different teams within a large enterprise and they figure out some business critical use case and they just go ahead and build embeddings for that specific use case. So they make infrastructure decisions that are very use case specific, because that makes sense. They want to quickly deliver value, and those decisions might be different from what other use case teams need. And so this might be the choice of your orchestration system, choice of where you're storing your embeddings, how you're generating embeddings. All of those things are made independently. And then finally, the stage bit that we're seeing the leading tech companies be at is company-wide platform-supported critical use cases. So that's where the central ML or AI platform teams recognize that there's several teams working on embeddings-related use cases, and they get the executive buy-in to build a high-performant and flexible system. They deliver operational efficiency, it's fully secure, governed, and the total cost of ownership is managed. So there's cost attribution. And so the use cases that I had just showed you at these leading tech companies are more closer to 3 or 4, depending on their different internal structures, but they're very much critical use cases and in production. So the rest of this conversation, we're going to focus on stage 3 and stage 4. So just to generalize, we looked at a few specific examples, but to just generalize on what people are embedding, there's these few different things among many, many others that are the most common. So for recommendation systems, whatever you're recommending, you can embed the titles, descriptions, the images, user reviews, or even the user itself. Like there's so much user data, you can just express those things in a numerical format. For search and ranking, the user query and object attributes are what people typically embed. For retrieval augmented generation, it's document chunks, some tables, PDFs, images, anything that you want to search over. For fraud detection, there's a whole host of things, but the most common ones are names, website data, transaction notes, transaction categories. And a lot of these things a lot of the other things are proprietary for fraud detection, but these are the most common ones. For insurance, there's things such as claim notes, policy documents, applicant profile. And for support, I'm talking specifically about high volume support, customer support use cases where you have just thousands, if not hundreds of thousands of call transcripts generated every day, chat messages, support documentation. So that would also qualify for a pretty business critical use case. All right, so I'll take a look at the questions. It seems like there's a few. Okay. What kind of data does Lift2Vec embed? Is it location or more data? So, Maury, that's a great question. So Lift2Vec was embedding a whole host of data. It was looking at the time of the day of the week. So for on the driver side, what time of the day are they most active? What days of the week are they most active? So there's a mode in Lyft on which direction you want to go. So it's like if you're done with your shift, which direction you want to go. So that's another thing. There's other features such as how many rides does a driver give in a week. So there's 100 different items for every single driver, probably even more. And similarly, there's a lot of information for geo hash sixes, which is the region. Um, the, for the region, it would be how many people are requesting it as a pickup location, as a drop off location, what hour of the day, what time of the week. So all of that information can be represented as an embedding, and then you can just compute similarity scores. Mukta asked about between cosine, dot product, and Euclidean distance. Is there a preference between all these? When to use which one? That's a good question too. We've seen cosine being used quite a bit, and I think the preference depends really on the use case and how you're embedding. So it's very use case specific. What is the intuition behind OS embedding models being better than the commercial providers? Um, that's a great question that I don't have a good answer for, actually. I mean, if you so there's a leaderboard that you can just look at. It's called the MTEB, so Massive Text Embeddings Benchmark, and you can just look at that benchmark and see how open source performs compared to paid. My intuition would be that embeddings models tend to be simpler and smaller than large language models, so you can easily build upon them on your own. So as an open source developer, I could just iterate on the current best open source model because it's smaller, maybe just a few 100 million parameters, compared to building my own LLM would require infrastructure that can support hundreds of billions of parameters these days. And so I think it's just a simpler task, and there's just been more investment. And then Eric, okay, Eric just responded. Great. Cool. So now that we've seen several examples of embeddings, and we've seen examples of embeddings being used for business critical tasks, let's take a look at some of the production challenges that people face when they try to run embeddings at a large scale. So there's two engineering stages that anyone running embeddings in production would have to deal with. So the first stage is called inference, second is called serving. Inference is just taking all of your data. It can be structured, unstructured, and using an embeddings model to get the numerical representation. So that's the inference stage. Serving is that given those numerical representations, you want to do point lookups or similarity searches. So point lookup is when you have A and you want to get the embedding for A, and similarity search is where you have an embedding and you want to get the similar items for that embedding. So let's first look at the production inference challenges. So there's 4 different categories of inference challenges that we've seen customers face. So the first one is compute resource management. Second is data pipeline orchestration. Third is training data generation. And finally, experimentation and reproducibility. So I'll go over each of these in more detail. So compute resource management refers to just running inference for millions of embeddings every day, which can be both computationally expensive and memory intensive. So in order to do this effectively at scale, you need very careful compute provisioning. So how to spin up and spin down GPUs. You need scheduling of when to run the different jobs. And then you also need to tune resources. So GPUs, there's just hundreds of ways in which you can optimize GPUs for different models, different model architectures. And so this is a significant task to just figure out which GPU to use, how to schedule it, and then which model to use with which GPU and which optimizations to turn on for which model. There's just lots of knobs here for compute resource management. And trial and error is expensive with this because, as you might be aware, GPUs are fairly expensive, and just running all these different kinds of tasks is costly. The second big inference challenge is data pipeline orchestration. So if you're productionizing your embeddings, you're eventually going to need data from many different sources. There's the real-time data that's coming from apps directly. There's the streaming data coming from Kafka, Kinesis, any other event stream. There's the batch data coming from your data warehouses, Snowflake or S3. And then there's also unstructured data, which might be living in any of these. So PDF, text, PNG. And so not only you have to orchestrate and connect to all these different data sources, you also have to connect them to the embeddings model, the training layer, the inference layer, and then finally the generated embeddings to the downstream AI pipelines. So there's a lot of connections to be made here, and all of them have to be properly managed, tested, maintained, and monitored. So all of this requires tedious data engineering, which is really hard to set up and manage. The other aspect of inference challenge is generating point-in-time accurate embeddings, training data efficiently at scale. So I want to spend a little time here. There's two worlds of how people are approaching AI modeling today. In one world where people follow a systematic approach where they generate training data and just see if how the historical predictions were made, and then they train their model. The second approach is where people sort of just use an LLM or a model provided by a third party, and they don't really evaluate anything historically as long as the current information is correct. So the second approach is more of this newer Wild West approach where people just work with prompts. I've seen examples of people adding "my grandma just died, oh LLM please like respond." So it's like different exploits, and they don't really back test any of the prompts on the historical data. Whereas the other more production ready approach is that you systematically evaluate on every historical event that you have, and you then basically measure and see which approach works the best. And you can do that both for generative and predictive AI. But for generative AI, I've seen use cases in the wild where people just sort of YOLO the productionization of it by just doing prompt engineering and deploying. So what does point-in-time accuracy mean? Point-in-time accuracy means that, let's say you had to make predictions for at different point of time. So these could also be generations, by the way. So let's say in the Lyft example, you had to make a prediction for matching a driver with a location at point in time A, B, C, and D. So at this point, you should have only considered the data that was available till then. And so this data might be the times that the driver was available in different regions just till that point. They might switch their patterns, but for training, you should only look at this data because that's when the prediction was made. And so what this means is that all of your labels or ground truth has to match the feature values which were present at the time of that prediction. So generating this point in time accurate embeddings training data efficiently at scale is an arduous process because your data is just continuously changing. So if you want to generate training data in a way that is point in time accurate, you'll have to do some really complex querying logic if you try to do it yourself. Another production inference challenge is experimentation and reproducibility. As I mentioned, there's a lot of complexity on the compute infra side, but there's also a lot of complexity on just the embedding model side. So there's many different embeddings models that are open source and available, and they're all good, but they're good for different things. There's also the inference performance. So how long does it take, and what kind of texts you can embed in a given amount of time. And then there's also the infrastructure costs. So you have to do a delicate dance of just identifying what's the most important to you and how much do you want to explore between embedding model complexity, performance, and costs. You also need a way to quickly test, evaluate, and refine the embeddings approach. There's many different approaches for if you're especially building your own embeddings models. There's ways in which you can really outperform any of the open source models by training on your own proprietary data. And for that, you need a way to just test, evaluate, and refine the approach. And finally, you need online offline consistency to run reliably um, in real time. So online offline consistency means that whatever you're training your model on is the same as whatever you're inferring the model on in real time. And the reason why people sometimes miss this online offline consistency is because in real time the events are coming from a stream or some real-time source, whereas when they train, the events might be coming from a data warehouse, and there's some skew in how the data is written, and so that can introduce just unreliability in how you're modeling. And especially if you're running these business critical use cases, you need all of these things to ensure that you can get the best performance at the best cost. On the serving side, there's a couple of different challenges. So there's the efficient storage and retrieval, and then there's the infrastructure scalability. So storage and retrieval is just dealing with storing or serving tens or even hundreds of millions of embeddings. So this will scale if you're doing recommendation systems, it scales with your items, or if you're doing fraud detection, it scales with your number of transactions. So whatever is your core entity in the business, uh, or your or any content that's being generated, that would be sort of the order of magnitude of how many embeddings you would need. So there's also the need for two retrieval patterns that I mentioned, point-based lookups by unique IDs. So these are for things if you're trying to classify, run fraud detection, or even if you're recommending something, you might want to just look up the embedding for it. And then there's similarity search for nearest matches to a query. So these are the two different patterns that you would need to support at scale. Both of these are hard to achieve low latency retrieval with optimized storage and cost. So you need specialized architecture. So an example here would be caching frequent embeddings. So let's say you have some items that are just really, let's say it's some Black Friday event and there's deals going on, and there are some items that are just very frequently accessed. You just want to cache those embeddings instead of recomputing or even like retrieving from the database, because all of those things have latency concerns, and latency really affects the performance of your end-to-end business application. So building infrastructure for large-scale storage and retrieval with all the cost optimizations is a challenge. And finally, there's the infrastructure scalability. So embeddings lookup volume can have irregular traffic patterns. So as I mentioned in the Black Friday example, you might have a spike of for embeddings, or even just other queries on your platform. And so there is a need for a solution to prevent performance degradation, but also you want to avoid over provisioning serving resources. So on one end, you want to just gracefully handle seasonality or spikes, and on the other hand, you want to just avoid paying extra costs for your serving resources. Apart from these serving and inference challenges, there's a few other operational challenges that customers, specifically large organizations, would face. So there's the collaboration on embeddings pipelines challenge. So typically, it's not just one data scientist working on generating embeddings. It's a team, or sometimes even many different teams that are going to use a given embedding. Let's say an item embedding. And so what you want to do is easily collaborate, share ideas, share code, and easily be able to see other people's work, even if you can't really edit it. And so this is an operational challenge that a lot of large organizations face. The second challenge is version controlling embeddings. This is actually fairly important because embeddings models can update not just the overall model, but the model version for a given family of models can frequently update. And when you update your embeddings model, you want all the downstream applications to also start using the newer embedding. So just keeping those synchronized when the application uses it and when the newer embeddings are generated is a challenge. And so you need some pretty high grade version control for this. There's the challenge of governance and lineage of embeddings. There's a need for just easily managing what's accessible and what's not by different teams, and just seeing the lineage of which data sources generate which embeddings, because some data sources might not be the golden data sources. So there needs to be some set of tooling for ensuring that only the right data sources are used for generating embeddings. And then finally, adhering to safety standards while leveraging open source is very important. And this open source is referring to embedding models, but also other things that you're going to have to deal with if you build all of this out for yourself. You'll have open source and orchestration systems, open source for tuning your GPUs, just lots of open source for setting up this whole production pipeline. So all of those things have vulnerabilities that keep coming up, version upgrades, and you have to adhere to safety standards. Okay, I'll take another look at the questions. Regarding point-based lookup, is Tecton offering anything similar to, say, MongoDB Atlas or Azure Cognitive Search, where there is both vector-based retrieval and traditional Lucene-style indexed, and the hybrid approach that combines the two? So I'll actually get to what Tecton is providing in the next set of slides. But the answer to your question is, like, the short answer is yes. We currently are providing point-based lookups with just key value, and we'll shortly provide vector search. So that's a good segue into our next section, which is Tecton embeddings. So Tecton embeddings is our capability for seamless embeddings lifecycle management to power production AI. And now that we have defined production AI and what that looks like in 5 leading tech companies and what are the challenges that they have to deal with, now we can talk about how Tecton solves these things. So Tecton over the past 5 years has built the best-in-class compute, storage, and serving for features. So features are just any other categorical numerical inputs to models. And we have been investing a lot of resources in just perfecting the feature platform. So we have a whole host of different data sources that we connect. We have all the capabilities around version control, logical definitions, discovering, using, monitoring, governing features. And what we've really done is we recently made embeddings a first-class entity. And that just meant adding a few different things. So we had to add support for unstructured data sources. We had to support a way to export to vector databases. And then we had to just evolve our compute engines, which were doing aggregations only before, to also run embeddings. And finally, we needed a way and more enablement to support generation and search use cases. So it was a very natural fit for us to support just another data type, which is embeddings. And we had to just make these incremental additions to our platform because we had invested so much time in just solving some of the production problems for features. So this is actually if there's one thing that you remember from this presentation, this is that message. Embeddings are essentially just model generated features. And so let me expand a little bit on that. So when we think of machine learning features as traditional machine learning features, they were hand engineered. So what that means is some data scientist has to specify some transformation. It could be a SQL query plus an aggregation. So an example of a classical feature is number of user transactions over the past 30 minutes. And so a data scientist would go and query the transactions table and then run an aggregation that does just a count. And in Tecton, it's really easy to express this in just a few, like 5 to 10 lines of code. And you can express many different complicated aggregations, last distinct n. So what are the last distinct items that a person viewed? So that would be another aggregation. But all of those classic ML features were hand engineered. It was a data scientist who was writing the logic. Data scientist or software engineer. Embeddings are model generated features. And what I mean by that is that now instead of specifying that logic and aggregation, you just say, here's my data, here's the model I want to use, give me the feature. So it's even shorter than generating features. You just have to specify the model and you get an embedding, which is not to say that it's easy to specify the model, because you have to do a bunch of evaluations and figure out what model to use. But once you have the model, it's just the model generated feature. So here's what we recently released in private preview. So embeddings generation is our first offering as part of the Tecton embeddings product. This is high performance, cost efficient generation, storage, and retrieval. So here's how easy it is to write production ready embeddings pipelines with Tecton's declarative interface. You just declare a batch feature view like any other Tecton batch feature view. The sources are your data sources that are connected with Tecton. Entities are logical representations. And this is the new part where you specify an embedding which looks at a column name. So this column name is coming from your transformation. So this could be a SQL or it could just be a data frame query. And then you specify your model. That's pretty much it. Before this, you might need to have more complex SQL here, plus run aggregations on them, and whoever is writing would need to know what's really going on and how it's aggregating. But now, once the model is selected, you just say, here's the text, give me the embedding. And with just 8 lines of code, you can very easily generate embeddings. And here we've used Snowflake Arctic Embed as the example. So this is a model which came out just late last month, and it's one of the top enterprise embedding models. They have published benchmarks on just enterprise related tasks, and so we very quickly integrated with it. And we also support a bunch of other top open source models. So what this gets you is integration with top open source models on Hugging Face, easy export to any vector database of choice. We have a very easy way of exporting to vector databases like Pinecone, Milvus, any of the top ones. And the reason why we chose this approach of exporting to any vector database is that we believe the vector databases are currently evolving really rapidly, and there's no clear winner that everyone is going towards. So across our customers, people had made different choices, and we wanted to support an approach which worked for everyone. And so we are starting with this approach of export embeddings generated with Tecton to your vector database, and then just query on your own. But in the very near future, we're going to add native search so that not only can you export to the vector database, but you can also just do both feature retrieval and similarity search just with Tecton connected to your vector database. So here's what the in-product lineage would look like once you apply this, the feature that I just showed, the embeddings feature view that I just showed. So you can connect with Snowflake. This is the batch feature view that I just showed. This can publish to the online store and offline store. And this is a feature service. So this is the most simplest lineage that you can have. If you're a Tecton customer on this call, you probably know of the really long lineage graph that you all probably have. And so you can use, in the same feature service, you can now have embeddings and features and other regular ML features and use them for both training and inference. And you get all of the benefits that you were already getting for ML features. So now we've seen customers have been talking to us for using Tecton embeddings for these type of valuable unstructured data. So product descriptions, customer feedback, transaction notes, claim summary, loan purpose, user posts for these type of applications, fraud detection, credit scoring, pricing, and so forth. And here are some of the open source models we've added. We're continuing to add more, and we're very open to just adding more models that customers ask us to add. So let's look at how all the challenges that I had mentioned are solved. I'll just quickly go over all the challenges I had mentioned and give you an overview of how we're solving. There's a lot more that's under the hood, but we just don't have enough time to cover it. So I'll keep it at a high level. So for compute resource management, we have built in a ton of optimizations like dynamic batching based on sequence length ordering, GPU-aware batch sizes. So these are very specific GPU optimizations that we've done. And because of that, our embeddings performance is excellent. We have had customers, our initial private preview customers who were running equivalent compute on other services, and we had, I think, close to 6x improvement for hundreds of, or I think close to a billion embeddings per day. So it's really, really high scale running on these very efficient GPUs at a much better cost performance. So they were just overwhelmingly positive reviews for the performance. On the data pipeline orchestration side, we already had great connections with Snowflake, S3, Kafka, the most common data sources. And we had connections with the online and offline stores. So now we have just enabled unstructured data formats. We are starting with text, but adding more data formats soon. So, but all of the pipeline orchestration capabilities that we have exist for embeddings too. Training data generation, as I mentioned, is very important for people who are building the AI and not just using a third-party AI provider. And so Tecton has been purpose-built for AI builders, and you can easily generate point-in-time correct training data with framework methods such as get features for events. And we have workflows for both prototyping in a notebook and productionizing in a way that it's online, offline consistent. So both data scientists and software engineers can choose their tools of choice. Finally, we have a whole ease of use to just iterate with confidence. You can just change a parameter name to get the optimized open source embeddings model. So as I mentioned in the previous example, we were using the Snowflake Arctic embed, but you could swap that with the all mini LM if you want a smaller model. If you could swap it with any other model name, and you can just rest assured that we're running the most optimal inference for that model, because for any model that we add, we optimize. Also, our features as code paradigm ensures that embeddings are reproducible and guarantees the online-offline consistency. On the serving side, you get both flexibility and efficiency. So you can pre-generate and serve embeddings or real-time generate embeddings. So if you are building a RAG application, you might need to generate embeddings in real time. We have the Tecton serving cache for accessing most frequently needed embeddings, and then you can also export to any vector store of choice. On the infrastructure scalability challenges, Tecton has been built with operational excellence as a guiding principle. So you can scale resources to meet spiky and seasonal increases for embeddings lookup volume with auto scaling. We also offer best-in-class availability SLAs, in-depth monitoring and alerting. And so all of your operational challenges are easily solved. So here's a very quick benchmark. We're probably going to make more benchmarks, but this is an early one that we ran on this open source Microsoft Marco V1.1 dataset on just a single NVIDIA A10 GPU. And it shows you for different models what was the tokens per second. So this is the smallest model that we have, all mini LM. And we are running 120,000 tokens per second, which is like a really, really fast embeddings inference speed. And even for larger models like the Snowflake Arctic embed, the model performance is several thousands of tokens per second. Another thing I want to highlight is something that's coming soon within the next couple of months is custom model inference. So we have heard from our customers that they want to bring their own embeddings model, especially the teams that are on the more just more on the level 3 and 4 stage. They have use cases where their models can outperform any open source models, or they just have input types which open source models are incompatible with. So examples here would be if you want to embed the text and category of an item together. So let's say you have some product description plus product color plus product size or price, and you want to embed that into the just a multidimensional product space, then you would need to create your own embedding model, and we will support the inference for that, and you'll get all the same benefits that I just outlined. There's also domain specific topic modeling. So these might be legal or healthcare related embeddings models, which are just fine tuned on data that customers have. And there's also just other models that are not even embedding models. So this can be a classification model. So sentiment analysis. So if you want to run sentiment analysis to generate a feature that will then be used for recommending something to a customer, you can just run the Tecton custom model inference. So you can just specify my sentiment model, the inputs it would take, and then the output name. And then this feature can be used for your end modeling task, which could be both predictive or generative AI. So what's next? I'll just give you very quick pointers on what we're building next. We're going to add native vector search with Tecton connected to popular vector databases. So currently our approach is to just export and you do the vector search yourself. But a better experience is if you could connect with the top vector databases and just do the search with Tecton. We're also going to add support for data types beyond text. So images, PDFs, audio, any data type. And there's also a lot more stuff that we'll reveal later that we're thinking, and that's more of the visionary stuff that we have. We're really excited to work on and talk about later. All right, that's pretty much it. Thanks everyone for tuning in, and I am happy to take questions. Okay, I'll look at the questions on the chat. So Mukta asked, assuming model parameter can have, yes. So once we have our custom models functionality launched in about a month or so, you'll be able to bring in any models. There's questions on the Q&A panel. Any comments on what data pre-processing, missing binning are needed before generating the embedded features? So there's a whole array of pre-processing techniques. Are you? I'm assuming you're asking about how Tecton would support it. So we will have a way of supporting some pre-processing in Tecton, but there's like just the number of things that you can do is sort of unbounded. So we'll have a separate later milestone where we'll support just natively pre-processing those things. But yes, you are right. There's pre-processing is needed for a lot of these use cases. Another question is by Maury is, can we replace embedding layers without fine-tuning or training the weights a full model if we do not use the publicly available versions? I'm not quite sure what that means. It seems like you're asking about the layers of the embedding model without fine-tuning or training. I'm not sure if that's something that can be done. I'm sure if it's an open source model, you could just do it because the source code is available and you can just change an embedding layer. But yeah, that's not something that we support in Tecton. Would you be able to share the presentation? Yes, we will. Yeah, it'll be on the Tecton website. Any other questions? All right. How about LGPD with our company proprietary data. I am not sure what that acronym stands for. I'm sorry, yeah, in the MLAI world, there's way too many acronyms, so I might not know what that is. I'm looking it up. Are you talking about the data protection law in Brazil? Okay. Um, I mean, Tecton. I'm not the person who works on like the GDPR side, but I can tell you we work with like some of our biggest customers are um, like large insurance companies, banks, financial institutions, and we are like best in class compliant with most regulations. So the answer is probably yes, but I'm not the expert there. But yeah, a lot of companies work connect their proprietary data to Tecton for us to process and generate features for. And we have different deployment models based on different security needs. And we also don't persist data at rest, so nothing gets stored with Tecton. Any thoughts on behavioral based embeddings, collaborative filtering? Would you generate them within Tecton? So collaborative filtering are basically the generation of embeddings is also sort of the training, if I'm not wrong, where you look at the user interactions and how different customers interacted. So when you're generating, you're also at the same time training. So that is a step that we will do eventually. It's the collaborative filtering is not directly supported just yet, but there are ways in which people are actually bringing in collaborative filtering embeddings to Tecton, where they run part of the pipeline on their end, so the training part, and then ingest the generated embeddings in Tecton through feature tables. So the short answer is that we will have that at some point, but currently there's a way of ingesting the behavioral based collaborative filter embeddings, and I'm specifically talking about use cases where the model artifact itself is very frequently changing. Um, a lot of people don't have that. If the model artifact is fairly static, then you can just give us or you can use Tecton's custom model inference that I just showed for generating those embeddings. Is there support for streaming features? Uh, yeah, I mean, we support streaming. Tecton has like the best offering for streaming features out there. Or are you talking about streaming feature embeddings? That will be supported too. We currently have batch and real time embeddings. We will have streaming embeddings very soon. But yeah, we do support just streaming features in general. All right. Thanks everyone again for tuning in. If you have more questions, take a look at our docs. They're very up to date with all the things that I talked about. And if you have any other questions, feel free to email me at mihir@tecton.ai. Thanks.